Morning, everyone. Thank you very much for joining us on this webinar, Data Sorting Operations in the Horner OCS. As usual, we'll have a Q&A session at the end, so please submit any questions you might have into the questions panel.
Hello and welcome to today's webinar. Today we're going to be looking at data sorting operations in the Horner OCS. Let's get started. Let's look at our agenda for today. We'll start by looking at some example applications. We'll look at how data sorting logic works in general, and then we'll see the data source user-defined function blocks that we've created. There will be demonstrations throughout, and we'll finish with a Q&A session. Here's an example of different applications for data sorting. Let's say we're using the OCS for machine control, but we're also using the OCS during a test mode of the equipment, maybe after we've done a machine changeover to a new part, or when we've just made some changes to our process control parameters. And we just want to make sure that everything's working properly. And we're going to execute a special test mode in the machine. So that might be a case where you're going to capture your process parameters, and then as part of your analysis, you might want to sort that process data in numerical order. Now we'll look at data sorting in a PLC, which is not done that often because it can be processor intensive, and for that reason, you often find it on computers offloading the PLC. However, we're going to show you today how you can do it quite easily and quite safely in the Horner OCS. We're going to use something called a bubble sort algorithm that we're going to apply in a user-defined function block so that you can use that UDFB to make sorting data much easier. So what is the bubble sort algorithm and how does it work? For example, say we have to sort data from low to high. We're going to use a bubble sort algorithm to do that inside of our user-defined function block. So you start at the beginning of a list of data, and then you start by comparing the first two values in your list. And if the first value is larger, you're going to swap the position of the two values. Then you'll move on to the next value in the list and compare again. Again, if the lower value of the two is larger, then you're going to swap. And so you'll keep going until there are no more values to compare on the list. Now you must go back to the start of the list and repeat. You go through the list in its entirety multiple times, and those are called passes. When there are no more values that need to be swapped, the process is complete. This is difficult in a PLC because you need to execute a loop, and in PLCs, loops can be problematic. If they're not handled carefully, you can end up with an infinite loop. Another reason it's difficult is you need to make multiple passes through a loop, so the larger the amount of data, the larger the array you need to sort, and the larger the number of passes that you need to go through the data to accomplish the sort. It can also have an impact on scan time. So in some cases, you'll find data sort routines in PLCs which are limited to a certain number of passes per scan. In our case, we're going to limit it to a certain size of an array to keep it from going wrong. Now we'll look at the Horner data source user-defined function blocks that we're introducing today. They're designed to make sorting data easy in a Horner OCS. Inside the user-defined function block, there's bubble sort logic looking at all the loops in the multiple passes, and the result is there are 6 UDFBs that we're making available, where you can sort up and sort down for all of integers, double integers, and real. So there are 6 different UDFBs available for you to use, depending on what data type you're using and whether you want to sort up or sort down. Now we'll look at the inputs and the outputs of the UDFB. So there's an enable input that must be on to enable the source. The way this routine works is it performs the sort on the first scan after the enable bit has been enabled, so it only takes one scan to do the sort. And after that, as the function block remains enabled, it does nothing as it's finished executing. The next input is the input array, which is the data that needs to be sorted. So you'll have an array of data, test results or production data, etc., and that will be the array that is going to be sorted. The function block doesn't touch the input array data, so that will remain intact when the sort is complete. The third thing to specify for the input is the length. How many elements in that input array need to be sorted, and we can support lengths of up to 100, which may be expanded in the future. On the output side of the UDFB, there's a done bit that tells you that the data has been sorted and that you have the output array. Another thing that's provided as an output is an integer value called pass count, which is how many passes through the data were required to sort the actual data that you just executed. So depending on how the data is arranged in the array, it may take a lot of passes or it may take only a few. And then finally, there's an error bit that can be set if you set the length parameter incorrectly. So if you forgot to set your length to a value greater than 0, or if you set it to a value greater than 100, then the error flag will turn on. So here's a schematic view of what's happening inside the user-defined function block. As soon as the block is enabled, it performs an error check, and then, provided the length parameter is set appropriately, it starts out by taking the input array data and copying it to the output array. So again, it doesn't touch the input array data, it just uses it as the initial source of all the data. Once it's copied into the output array, again, it starts out in the exact same order as it was presented in the input array. Then we start going through and making passes and rearranging the data. So again, we start by comparing the first two values in the list. If the lower value is larger, we perform a swap. This is the logic if you're arranging from low to high value. And then we just keep on moving through the array until we get to the end. And if we get to the end and we had to do at least one swap, we do another pass and keep making passes until we don't have to do any swapping through one complete pass, and then we're done. So that's the diagram of what's happening inside the logic. Now we'll go to Cscape. Firstly, we'll look at the user-defined function block, which is available through the UDFB section of the toolbox, but it's only there because it's been imported. To import it, we go to the Logic Modules area of the project navigator, we right-click and press Import Logic Module. Then you navigate to the folder containing the CPU file and type in star.cpu so that it can find any CPU files, select the one we want, and then press open and it will import it. Once you've imported it, it shows up under UDFB modules, and then after that it's available from the toolbox, so you can just click it and drag it into your project. But here we already have one in use. So once the UDFB is on your desktop, the first thing to do is name it, as one of the advantages of having user-defined function blocks is that you can have multiple instances of them in the same program. So if there are 2 or 3 different arrays that you need to sort, you can have 2 or 3 different data source UDFBs that you're using in your program, one per array that needs to be sorted. Then you just assign your input variables and your output variables. Those don't have to be variables, but in this case we do assign a variable here. So here's the array of data, and whenever we specify an array with UDFB, we always specify the first element in the array. So that's element 0 here. So this is the input data that's going to be sorted, and then we've also specified as an output array another array because we leave the input data intact, but we copy it as part of the logic inside the UDFB. And then we perform the sorting and report the sorted data as the result array. Then we have an enable bit as well as an error bit, etc. So that's how you'd apply it. Now we'll have a look through the logic inside the UDFB. For some this is irrelevant because you can just use the user-defined function block and you don't need to worry about the logic inside the block, but we'll look at it anyway. So inside the UDFB, when the function block is not enabled, all the output variables are set to 0. So that's the first thing that happens. We mentioned earlier that all the looping and all the passes we make in the UDFB to perform the sort are all done on a single logic scan. So what we do here is we turn on a one-shot bit that we're going to use for all the logic as we're going through our loops. That tells us that this is the first scan after the enable. So then it's time to execute the logic. Once we've established the one-shot, the first step is to check the array length. It should be within a valid range, not 0 and not exceeding 100. If either case is true, we set an error bit and immediately jump to the end. Another instance where we jump to the end without further reaction is during the second pass after enabling the function block. There's no need to repeatedly resort the same data as it wastes CPU time. From the second pass onwards, it will always jump to the end. However, on the first pass, there is work to be done. We start by setting the initial index values, as loops in any programming language require an index to progress through the loop. After initializing the variables, the initial logic consists of a short loop that copies the input array to the output array. The input array remains unchanged, and the output array mirrors the original order. Next, we enter the main logic where multiple passes are performed. At the beginning of each pass, the indexes are reset to their initial values. During the pass, we load values for comparison, compare them, and determine if swapping is necessary. If a swap is required, a flag is set to indicate that at least one swap occurred, meaning another pass will be needed in the future. Once we exit the loop, we check if a swap occurred during the previous pass. If no swaps happened after several passes, we consider the sorting complete. That's what happens inside the UDFB. However, all you need to focus on is using the UDFB as we showed you earlier. Now we'll go to the benchtop for a demonstration. So here we'll start with a small array of test data containing only 10 initial elements or data values. In the first column, you can see that the values that were originally captured. In the next column, we have the sorted values. At this stage, we haven't enabled our UDFB, so all the values remain fixed at 0. Now, if you forget to select the length in the sort routine for the UDFB and then try to start the tasks, we just immediately get an error because again, the length has to be greater than 0 and not greater than 100. So we'll start with a 10-piece sort here. So we press the start button and our result is we've sorted the data from least to greatest, which is the sort we wanted to accomplish here. We can see it took 7 passes through the data to get everything completely sorted. Now we'll look at another scenario where there's a bit more data. So we could show 100 values on the test screen here, but the print would be small. So instead, we see the first 10 values and the last 10 values. So the middle part of the array from index 10 to index 89 is not shown on the screen. Here we have similar data to what we saw before, and then mostly zeros everywhere else. So after we sort this data, we should see the non-zero values show up towards the top and the zero values towards the bottom. So we'll change the amount of values to sort to 100, and then we'll perform the sort. So now we see the low values, and they're in the low part of the sorted data. And then are the non-zero values, which are at the top end, because we only had 10 non-zero values, and the other 90 values were all zero. If we want to see this in a graph, it's easily done. So we'll turn on the graph screen here, and we'll press the graph results button here in the example. And you can see that in red here, we have a look at the data from least to greatest, and we can see that a vast majority of the data during the test was zero, but that we also got some values ranging all the way up to near 1000. So for certain types of testing that you could be doing, this could be useful information. So this is a way that you can quite easily sort data in a Horner OCS, and as a result of that, graph the results. Data sorting is a useful function that is often reserved for computers instead of PLCs, and that's because they can be processor intensive and have the potential to impact your scan time. The data sorting UDFBs provide a practical means of sorting data values on arrays with a dimension of up to 100. So that concludes today's webinar. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, there's no questions there at the moment, so I really hope that the presentation this morning was useful for everyone. Next week, we're going to have a session reviewing the available licensed features on the Horner OCS. You can register for that webinar on the Horner website in the webinar section as usual. So thank you everyone very much for joining this morning, and have a good day.